We are going to close off Physics 122 by discussing Maxwell's equations and electromagnetic waves. Maxwell's equations are a set of four equations, or they could even be written as a set of two equations, which, when combined with the value for the fundamental charge, 1.6 times 10 to the negative 19 Coulomb, contain all the information there is to know about the topic of classical electricity and magnetism. Previously, we wrote Ampere's law in this form. So when we write Ampere's law, we are considering that we walk in some closed loop where B is the strength of the magnetic field at our location, L is the size of a step we take as we are walking around a closed loop, theta is the angle between the direction of the magnetic field and the direction of a step that we take, and I enclosed is the total current that we walk around as we traverse our closed loop. Now, in this picture, I just chose to draw a current from a very long wire that is flowing into the computer screen. The magnetic field from the right-hand rule will wrap around the wire in a clockwise direction. The path we chose to walk is a circle that is always the same distance, where we are always the same distance from the wire. So we are walking in a circular path centered on the wire. Now, there is no fundamental reason why I was required to choose this path as I drew it on this picture, but when we proved the strength of the magnetic field from a long straight wire, when we proved the strength of a magnetic field inside a solenoid, it turns out that some paths are more convenient to work with than others when you're working with Ampere's law. So it is convenient that if we're always the same distance from the wire, we're always going to have the same strength as the magnetic field. If we're walking in a clockwise loop around the wire and the magnetic field is clockwise around the wire, the direction of every step we take will always be parallel with the direction of the magnetic field. And working with cosine of 0 or cosine of 90 is always a very convenient choice. So there's no reason why I couldn't have chosen to walk in a square path or something else for this particular setup. But as we saw when we derived the strength of the magnetic field in those two scenarios from the previous chapter, from 2 chapters ago, the type of path we take does matter in terms of simplifying our lives very much. So let's consider this circuit. This is an RC circuit that we saw previously back in for exam 2. And let's apply Ampere's law to an RC circuit. So what we're going to do is we're going to connect a capacitor to a battery. The battery will be pushing charges through the wires, and then the charges will be accumulating on the plates of the capacitor. Now, there's no reason we need a resistor in this circuit. What we're really interested in is watching what happens when the charges are being placed onto the capacitor plates. But I want the charges to I do not want the capacitor to fill up instantly. I want the capacitor to slowly fill up. It'll help me watch what's going on, so I put a resistor in there. We don't really need the resistor, but we just don't want the capacitor to fill up too rapidly. Now, if I were to apply Ampere's law right here, well, here's a loop. I have a current flowing, so I'll have some magnetic field. Because I have some wires, the magnetic field might be in a direction that's not just perfectly wrapped in the same direction as my loop, but maybe if these wires are really big, maybe it will be a good approximation. Okay, there's nothing wrong with that. What will happen if I choose my closed loop that I study when I look at Ampere's law to be between the capacitor plates, or the closed loop is somehow where there is no current flowing through the loop? Here, I very explicitly could see there's a current passing through the loop that I walk. But in this scenario, I'm going to have the capacitor on either side of my loop, so I don't have a proper current flowing through my loop. What will this look like when I apply Ampere's law? Now, for this discussion, we want to make this discussion relatively simple. We're going to assume that our loop the plane of our loop is parallel with the capacitor plates. We're going to allow our loop also to be larger than the circumference or perimeter of our capacitor plates. So a picture with perspective of what our loop really looks like is going to be something more like this. So we have our capacitor plates that are acquiring their positive and negative charges, and our loop is parallel with the plates but larger than them. The same picture but from a different perspective might look something like this. So these are just two different perspectives of the loop in this charging RC circuit that we're going to walk around and we're going to apply Ampere's law to. Now, very explicitly from the picture that I've drawn, there is no current passing through the plane of this loop. Well, if there's no current passing through the plane of this loop, then I enclosed is going to be 0. So the entire right-hand side of Ampere's law appears for the moment like it's going to be 0. But this isn't going to be the full story, so let's investigate this more closely. Now, if there is no loop between the plate, if our loop is between the plates, there is no proper current flowing through the loop, so I can correctly write that I enclosed is going to be 0. But there's going to be something else going on. As the capacitor plates are acquiring charge, well, we saw in chapter 17, Q equals CV. So as the capacitor plates acquire charge, there will be a growing voltage between the capacitor plates. And also in chapter 17, we saw that as the voltage between the plates grows, there will be a growing electric field between the capacitor plates. So the charge on the plates grows will cause a growing electric field between the plates. Now from here, I could write Q is equal to C times V. So voltage is E times D between the plates of a capacitor. From chapter 17, we saw this. And this Q is growing with time. Originally, the plates of the capacitor have no charge on them, but as time moves on, they're getting more and more charge. So if I were to look at the rate at which charge is being deposited onto the plates, the rate at which charge on the plates is growing is delta Q over delta T. Well, if I put a delta T on in the denominator on the left-hand side, I have to do the same thing to the right-hand side. If I look at every term on the right-hand side of this line, C is the capacitance of the capacitor. That's just a constant. D is the distance between the plates. That's just a constant. E is the electric field between the plates. That is not going to be constant. As charge grows, voltage grows. As if voltage is growing, then electric field is growing. So the rate at which charge is deposited onto the plates is equal to the rate at which the electric field grows times C and D, which are constant in this problem. Now here, delta Q over delta T is not a proper current. A current is moving charges, usually in a wire. So delta Q over delta T is not a proper current, but it's kind of like a current because it is the rate at which charges are being deposited onto the plates, and it is causing the electric field between the plates to grow. So since, as I said, C and D are constant, I'm not going to worry about them. That's why I don't really need to put the delta T in the denominator. I don't need to include C and D. And delta Q over delta D does kind of look like a current, so I'm going to call this term quote-unquote I. And we're going to investigate what is the nature of this quote-unquote I. So I could say quote-unquote I is equal to the capacitance times the distance between the plates times the rate at which the electric field between the plates grows. Now, it's not obvious why this is going to be useful, but there's no rule that says we can't do this. Let's multiply both sides of this equation by A. A is the area of the capacitor plates. If I do something to one side, I have to do it to the other, so I'm going to do that. Okay, I will get something like this. Let's also move the d to the left-hand side, so I'm going to divide by d, the distance between the plates, and I'm going to multiply both sides of this equation by epsilon naught, the permittivity of vacuum that we saw way back around the time of exam 1. So if I bring the d on the right side into the denominator on the left side, multiply both sides by epsilon naught, I get a term that looks something like this. If I look at this line for a moment, I realize I have epsilon naught A over D. That's just the capacitance of a parallel plate capacitor. So epsilon naught A over D is the capacitance of my capacitor, and I also have a C right here. So I could cancel these terms out. And what I'm left with is this quote-unquote I is equal to epsilon naught times the rate at which the electric field grows times the area of the capacitor plates. So for parallel plate capacitors, when we work with parallel plate capacitors, we assume that the electric field between the plates is going to be 0 everywhere except between the plates. So when I work with parallel plate capacitors, we have Q equals CV, V equals ED. So when I work with parallel plate capacitors, I could write the Q is equal to C times E times D. I could rearrange to solve for E, and I get a term that looks like Q over C times D. So the electric field between the plates has a value that is not 0. Everywhere else, the electric field is 0. Now, A is just the surface area of the capacitor plates. If I want, I could bring A up here in the numerator. A is a constant, so it's not going to change anything if it's in the numerator or not. And if I write this quote-unquote I is epsilon naught delta EA over delta T, well, E times A is the electric flux over my loop. So the total electric flux over the loop that I travel around is E times A. And so this term here is the rate at which the electric flux is growing. So because E electric field is 0 everywhere outside the plates and electric field is non-zero everywhere inside the plates, the electric field in the region where the plates are is the only thing that's going to contribute to the growing electric flux. So this quote-unquote I, this thing that resembles a current but isn't really a current, is kind of like the rate at which an electric flux grows. So if you think back to the previous chapter, we talked about magnetic flux, change in magnetic flux, the rate at which magnetic flux changes. This term here in the fraction is the rate at which an electric flux is changing. So this thing that is behaving like a current, even though it's not a proper current, is a growing or decaying electric flux. So if the area of the plates is constant, which is generally the case for capacitors, but the electric field is increasing, I get this thing that resembles a current is the epsilon naught, the fundamental constant of nature, times the rate at which the electric flux is changing. Now, for parallel plate capacitors, as I said, we assume the electric field is 0 everywhere except between the plates. So this quantity that kind of looks like a current but isn't truly a current, I call a displacement current. So displacement current is defined as the rate of change of electric flux multiplied by epsilon naught. Now, the rate of change of electric flux might sound like this really weird, obscure quantity, but you've been working with the rate of change of magnetic flux a lot in the previous chapter. So to understand the rate of change of electric flux, just think about it in the exact same way as you did in the previous chapter with magnetic flux, but now instead of talking about magnetic flux, we're going to be talking about electric flux. So how will displacement current fit into Ampere's law? What are we going to really be doing with it? Well, I enclosed on the right-hand side of Ampere's law is defined as the current passing through the surface whose boundary is the closed loop. So way back when, at the beginning of this discussion, we said, okay, I have a current passing through the surface. Here's my loop. So the loop that I walk is the boundary of my surface. Here's a loop. So this loop must be the boundary of my surface. But we were not specific as to what surface we are restricted to use. As long as this square, this loop that I walk around, is the boundary of the surface, I'm okay. So one possible surface I could talk about is this surface right here. So here I have just a flat plane. The flat plane is my surface that is parallel with the plates of the capacitor. I clearly do not have any traditional current passing through this surface, but I do have this new thing called a displacement current that I talked about. In this case, I would say the enclosed current, the traditional electric current that we've talked about since January, is 0, but I do have a displacement current through this surface that is non-zero. But what if I want to be cheeky and choose a different surface? As long as the boundary is defined by the path I walk, I'm allowed to choose a different surface. What if I choose a surface that looks something like this? So now the surface is 5 sides of a rectangular solid, and the boundary is still the path I walk. Previously, this was the surface. Now that side is empty, but I have the 5 other sides of a rectangular solid. Well, in this case, I do have an enclosed current. The path I am walking around is the boundary of a surface. The surface does not exist in the plane that is parallel with the capacitor plates. The surface extends behind the capacitor plates and cuts down through the wire. And in this scenario, I will have a current flowing through my surface again. So in this case, I could say, well, the displacement current is 0 because there is no electric field passing through my surface. The boundary of my surface is this path I walk. The surface extends back and down through where the wire is. I have no displacement current passing through my surface because I never have an electric field. So I'll never have an electric field that's changing. I'll never have a changing electric flux. But I do have a traditional current now passing through this surface. So here we have 2 scenarios. Neither of these scenarios violate Ampere's law. We are still required to have the path I walk be a boundary. In one case, I have the simple scenario where the path I walk just defines a flat plane. Here the path I walk is the boundary, but my surface I choose to wrap behind the plates of the capacitor. Ampere's law doesn't make any restrictions on what surfaces are allowed other than the path I walk must be the boundary. So both of these possibilities must be valid for Ampere's law to apply. In this case, we could resolve and reconcile this by saying both surfaces must be allowed. So Ampere's law we will extend to allow for displacement currents. So the full form of Ampere's law, we're not replacing Ampere's law, we're just changing Ampere's law. So Ampere's law could be written in its fullest form as this. So B delta L cos theta around a closed loop, we're not changing anything we talked about before with the left-hand side, is equal to mu naught times I enclosed plus I displacement. And where I enclosed is a traditional current, charges flowing through a wire, I displacement is epsilon naught times the rate at which the electric flux through that surface is changing. And again, electric flux, rate of change of electric flux, that is basically, you could think of it in the same way as magnetic flux, rate of change of magnetic flux. All you have to do is, instead of electric flux, you're dealing with, or instead of magnetic flux, you're now dealing with electric flux, but still the same principle. I'm going to move away from Ampere's law now and take a moment to talk about Faraday's law of induced EMF from the previous chapter. So in the previous chapter, we said that if I have a loop of wire and I move a magnet around near that wire, through that loop of wire, there will be a changing magnetic flux. And that changing magnetic flux will imply the existence of an induced voltage. If I have an induced voltage, Ohm's law implies I will have an induced current. And due to the relationship between current and magnetic fields, that implies I will have a second or an induced magnetic field as well. Now, earlier in 122 also, we discussed why charges move through a wire on the microscopic scale. If you want to get anything to move, you have to give it a push. So charges move because we set up an electric field and the charges see that electric field and they feel a Coulomb force, so they react to that electric field and move around in the wire. So on average, the direction that the charges are going to move is going to be in the same direction as the electric field we set up in that wire. So we could also just as well say that the changing magnetic flux will set up an induced electric field in the wire, and the charges will move in the direction of that induced electric field. So we also have an electric field flowing around this wire as the current being induced is flowing around that wire as well. So we could ask the question, how much work, or in other words, how much energy would it take to move a charge once around the loop of wire? So suppose we have a charge at the bottom of the loop. How much work do I have to do to get that charge to make one complete circuit around the wire? Well, we said the work done pushing something through a displacement is FD cosine theta. This was an equation we worked with a lot in the fall semester. The charged particles that are moving around the loop, they are being pushed on by the Coulomb force, so the force that we're going to consider is Q times E. So the induced voltage will imply the existence of an induced electric field in the wire, and the induced electric field is responsible for the Coulomb force that will get this charge to move once around the wire. So we are going to track the amount of work it takes to get a single charge to move once around this closed loop of wire. The Coulomb force is the force responsible for pushing the charge, so I could replace F with Q times E, and the direction of the force that the force is going to push the charge will be the direction the charge moves. So the direction of the force will be around the wire, the same direction as the induced current. Because the direction of the force is the same direction of the charge's displacement, I could say though the force vector and the displacement vector are parallel. That will cause the cosine of theta to become cosine of 0, which is just equal to 1. And so I could write the work done in moving the charge once around the wire is Q times E times D. Now, I'm going to set this aside for the moment. We'll come back to it. From Physics 121, we also said the work done in moving an object is the changing object's kinetic energy. So we could write that as negative delta PE. And when we wanted to bring in energy into problems involving electric charge, we had delta PE is equal to Q delta V. So I could write the work it takes to move a charge once around this loop of wire as QED, or I could write the work it takes to move the charge once around the loop of wire as negative Q delta V. So if I set these two equal to each other, because these both are just two different ways of writing the work it takes for my charge to move once around the wire, I could say negative Q delta V is equal to Q times E times D. Q is the charge of the particle that is moving around this loop of wire. I see Q on both sides, so I could cancel out the Q's. Also, what is this voltage? What is this delta V? Well, V here is the induced voltage. I move around my magnet, I get an induced voltage. Because the induced voltage is the rate of change of magnetic flux, I could replace this delta V with a rate of change of magnetic flux. And when I do that, I will get a form of Faraday's law that I will find very useful for the next example problem we're going to work through. Now, before I show you that the form of Faraday's law we're going to use, let's also remember that as this charge moves around the wire, I could think of moving in a closed loop as the sum of many small steps. And when I add up all those small steps together, I come back to my starting point. I've walked once around the wire. So I could write Faraday's law as when I move around a closed loop, E delta L cos theta is equal to negative rate of change of magnetic flux. So within this, here we have our electric field, which we wrote right here. Here, D was the displacement as we move around the wire. D here, in some of the previous slides when we talked about Ampere's law, we used lowercase d to represent the distance between some capacitor plates. Here, this lowercase d is the displacement the charge moves, so basically the distance around the wire. So here we have our strength of our electric field, the size of a step, but we're taking many steps which will add up to moving around a closed loop. And I want to be general, so I am allowing this cosine theta back in over here. On the other side of Faraday's law, I have the rate of change of magnetic flux being my delta V. So the Maxwell's equations are a set of 4 equations, and all of classical electricity and magnetism in vacuum could be described by the 4 Maxwell's equations that we've presented in this course. So we have Ampere's law and Faraday's law, and Ampere's law and Faraday's law look very similar to each other. On both of these equations, on the left-hand side, we're walking around a closed loop. We have a vector field. For Ampere's law, our vector field is the magnetic field. For Faraday's law, our vector field is the electric field. But we have a vector field multiplied by the step we take. In both of those cases, we're walking around a closed loop. And we have a term for the angle between the direction of our step and the direction of the vector field, whichever one it is. On the right-hand side of Faraday's law and Ampere's law, the displacement current was the rate of change of electric flux. Here we have the rate of change of magnetic flux. Now, we also have a traditional current moving charges through a wire in Ampere's law. We don't have an analogous term in Faraday's law, but these 2 equations look very similar to each other. Similarly, the other 2 Maxwell's equations are Gauss's law for electric and magnetic fields. If you have a closed surface, the total flux through that closed surface will be equal to the amount of charge inside that surface. If I'm considering electric flux, I'll have some electric charges inside that surface. Well, there's no such thing as magnetic flux, so it is impossible to put a closed surface around something where there's more magnetic fields exiting than entering that surface. So these 4 equations, combined with the textbook value of the elementary charge, contain everything there is to know about classical electricity and magnetism. Now, here I have the Maxwell equations written in one form, but if you prefer, it is possible to tattoo the Maxwell's equations in a differential form, or it is also possible to tattoo the Maxwell's equations in an integral form.